So yesterday we talked about one of the physical attributes of square matrices, this thing called a determinant. And for our purposes, it's just a unique number that's attached to a square matrix. But we saw that we could actually do stuff with that number. Yesterday we saw that we can use that number to find area of triangles. Today we're going to talk about another application of determinants, and that is to solve systems of equations. Now, I know we've talked about systems of equations in the first half of this unit. We talked about substitution and elimination, and indeed, those guys are still valid, those techniques. Cramer's rule is just another technique that you can possibly use. Admittedly, it is a little bit more tedious in some respect, but it's a good rule in case, it's a good rule to use if your system, say has a lot of fractions, or if you have a big system and you don't really want to solve the whole piece, you just want to know one specific answer. So it's still sort of nice to know, and heck, it's fun to play around with. So what is Cramer's rule, and how can we use it to solve systems? The first thing I want to sort of talk about is a little bit of vocabulary word. There's this thing in the world of matrices called a coefficient matrix. And I'm sorry, the definition is going to be very, very boring. What is a coefficient matrix? It's a matrix of coefficients. It is what it sounds like, right? For a linear system, some number times x plus some number times y equals some number e, and then another number cx plus dy equals f. Right? So A, B, C, D, E, and F they stand for regular numbers. For a linear system, the coefficient matrix would be A, B, C, D. Okay? So you literally see how all we did was we made a matrix by taking the numbers in front of the variables and putting them inside of a matrix. So that's what a coefficient matrix is. Pretty simple idea. You guys see how in this coefficient matrix, you guys see how A and C are the numbers in front of the x's? See how A and C are in this column? So in a coefficient matrix, you can sort of think of it as the first column being the x column, the second column being the y column. So by definition, or rather, let's say this. If A equals the coefficient matrix, which is A, B, C, D, then define A sub x as the matrix with the constants replacing the x column. What the heck does that mean? Well, if we take a look at the original system, ax plus by equals e, cx plus dy equals ef, these guys are the constants here. Do you guys agree that e and f do not have variables attached to them? So they're the constants. What a sub x is taking the coefficient matrix, but taking these constants here and replacing it in the x column. So in other words, A sub x equals, don't write this down because I'm going to do some erasing. I'll tell you when to write it down. It's taking the original coefficient matrix, right? But what you do is you erase the x column and you put in the constants of the problem. So here are the original constants in the x column. Does that make sense? Similarly, we're going to define a sub y. Again, I'm going to write down the original coefficient matrix, but I'm going to erase it, so copy it down after I do the erasing. A sub y is just taking the coefficient matrix, A, B, C, D, but you erase the y column and put the constants in. So does A sub x, A sub y, does that make sense to everyone what I'm doing? Take the coefficient matrix, and then you're just replacing whatever column with the constants. So do we understand the vocabulary word and the definitions? We know what a coefficient matrix is. We know what A sub x is. We know what A sub y is. All right. So here's Cramer's rule. Yes. Question.
Does it matter, like, can E be where F is and F be where E is?
The question was, doesn't matter the order. Can E be where F is and F be where E is? Order does matter. It needs to match the order of the original problem. Right. So order does matter in this case. So Cramer's rule. How can I use these matrices to solve a system? Cramer rule states, for a generic system, ax plus by equals e, cx plus dy equals f. I'm just rewriting the definition, guys. And A is the coefficient matrix, A, B, C, D. Ax is E, F, B, D. AY is A, C, E, F. So those are just the same definitions we did above. For any system, you can create these matrices, and therefore, the X answer is just the determinant of the AX matrix divided by the determinant of the original A matrix. And the Y answer is the determinant of the AY matrix divided by the determinant of the A matrix. It ends up being, this is a true statement, which is a pretty cool idea that you can use determinants of matrices to solve systems. Who would have thought? Well, I guess Gabriel Cramer thought of it because he's the one who came up with it, and that's why we name it after him. Now, if all these letters are too confusing, hey, Mr. Rowe, this is too abstract for me. I don't know what's going on. An example is worth 1,000 words. So let's see this guy in action with actual numbers with an actual example. Right. Again, I'm not saying forget elimination. I'm not saying forget substitution. Those are methods, good methods to know. I'm just providing you with lots of different options to solve systems. So let's go ahead and solve. Let's go back to the first half of the unit. Say 3x plus 5y equals 3, negative x plus 2y equals 10. Let's pretend, oh no, I forgot elimination, I forgot substitution, or let's pretend, you know what, I don't like those two methods. How can I solve this? Well, let's set up our matrices. So let's find the determinant of the coefficient matrix. So the determinant of A is the determinant of 3, 5, negative 1, 2. Are we okay with where I got those numbers? Right. So this is just yesterday's lesson, crisscross subtract. Let's see if we can do this in our heads. 6 minus a negative 5 would be a positive 11. A determinant of A sub x is taking the A matrix, but taking these numbers and substituting into the x column. So that's going to be a 3. That's going to be a 310 in the x column with the 5, 2 staying the same. Let's see if we can't do this in our heads. 6 minus 50, which is negative 44. And let's do the AY matrix. So that's, again, taking these numbers and substituting it into the y column. So that means the 3, negative 1 stays the same, but the 310 goes into the y column. So you go ahead, let's see if we can do this mentally. 30 minus a negative 3, which is a 33. So I have my answers. X is just the determinant of AX over A. which is negative 44 over 11. Hey, that gives us a negative 4. Y is just the determinant of AY over the determinant of A, which is 33 over 11. Hey, that's 3. We solved it. That's our answer, x comma y. Right. So it's just a different method to solve a system. If you don't like substitution and elimination, Cramer's rule will work as well. Right. Again, it's a nice method to use if you only care about one answer. Let's say you had a problem that had like 5 variables, 6 variables. That would be a pain in the butt to solve. But if the question says, hey, what does, z equals? You don't have to solve the whole problem. You can just use Cramer's rule to pinpoint a solution. So an analogy I like is solving a system using like elimination and substitution. That's like doing surgery with a bone saw, right? You'll get the job done. You just did the whole messy operation. Cramer's rule is like a scalpel. You're very precise, pinpoint. Cramer's rule also works for 3x3s. You just have to extend the idea. Instead of having an a sub x and a sub y, you're also going to have an a sub z, and a sub z is just taking the constants and putting in the z column. Does that make sense? Right. The only difference is it's just a bigger problem. That's all. So just for the sake of completeness, let's do a 3 equation, 3 variables example. Say, I don't know, x plus z equals 8. 6x plus 3y minus z equals 4. 2x plus y plus 3z equals 18. Right. So let's do the determinant of, let's do A, determinant of A. So that's going to be 1. Notice I'm missing a y here, so that's going to be a 0. 0, 1. 6, 3, negative 1, 2, 1, and a 3. Right. This one I can't do in my head, so I have to actually write it out. So I'll go ahead and copy the first 2 on the outside, 1, 0, 6, 3, 2, 1. And let's do our diagonals here. So that's going to be a 9. This is going to be a 0. This will be a 6 minus, this will be a 6, this will be a negative 1, and this will be a 0. Okay. So that gives us 15 minus 7, no, minus 5, excuse me, which gives us 10. Not too bad. That wasn't too horrible. Now we just got to do a sub x, a sub y, and a sub z. So a sub x is just taking the x column and replacing it with the constants here. So the x column will be 8, 4, 18, and then everything else stays the same. 0, 3, 1, 1, negative 1, 3, and then just repeat the process. So I hope I can do this without color coding it, because switching the colors, oh, I forgot to copy the columns. So again, I hope I can do this without color coding. That's going to give me a 72. This is going to give me a 0. And this is going to give me a 4. Do the other direction. That's going to give me a 54. This is going to give me a negative 8. And the last diagonal will give us a 0. So that's what? 76 minus, what's that? 46? Which equals 30. And then just repeat a sub y. So the x column stays the same, 1, 6, 2. And then the y column becomes 8, 4, 18. and 1, negative 1, 3. Do you guys get the idea? Can I just like fast forward through the answer? So if you did do the diagonals, if you did copy it, the columns, you're going to get a negative 30 here. And then a sub y, or a sub z, excuse me. The x stays the same, 1, 6, 2. The y stayed the same, 0, 3, 1. But the z's become 8, 4, 18. And then if you did that correctly, I'm going to fast forward through it. I think you guys know how to do determinants. If you fast forward through it, that's going to give you a 50. So now you know you can immediately just divide to figure out what x, y, and z are. So x was the determinant of ax, 30, over the determinant of a, 10. Y was the determinant of ay, negative 30, over the determinant of a, 10. And z was the determinant of az, 50, over the determinant of a, 10. So that gives you a 3, negative 3, and 5. So my answers are 3, negative 3, and 5. So you can see, yeah, it could be a bit longer, but I think it's easier. I don't know. I think crisscross subtract, finding determinant, might be easier than doing substitution or elimination, especially for these three big, like the three equations, three variables. Question?
I was genuinely lost on how you set up the equation. I tried to make sense of it.
You mean the matrices?
Yeah. That.
Okay.
The first one, A.
Uh-huh.
The first column was 1, 6, 2.
Yep.
And I think you got that from the 1x, 6x,
Yep.
2.
The A is the coefficient matrix. The numbers literally come from the problem. So here are all the x's. Here's the x numbers. Here are the y's. Now, you see how there's no y's here on the first equation, right? So that's a 0. Here are the y numbers, 0, 3, 1, 0, 3, 1. And then the z numbers, 1, negative 1, 3, 1, negative 1, 3. So that's how you do A. You literally just, it's called the coefficient matrix. You literally take the numbers in front. Do you know how we set up the A sub x, A sub y, A sub z?
That one I thought you could do it backwards, forward.
It's not backwards. It's taking this matrix, right, the A matrix, and you're going to take these numbers, and you're going to substitute it into the variable column. So A sub x takes those numbers and put it into the x column. So that's why you see these numbers in the x column.
So for the variable we're trying to, we're going to replace those numbers.
So the A sub x, A sub y, A sub z, whatever variable you're solving for, you're going to take the constant numbers and substitute it into the correct column. That's how you do A sub x, A sub y, A sub z. Okay? So for today's practice and today's practice only, I want you to try Cramer's rule on quizzes and tests. I'm not going to be picky. You guys solve it however you want. But give Cramer's rule a shot. Maybe you'll learn to like it. And if after today you go, I hate this, I never want to do this again, that's totally fine. But for the second half of 3.9, 3.9b, that is an application of determinants, solving systems using Cramer's rule.